Okay, so C stands for speed of light. It's a constant. You should have that on your card. Make sure you do. C equals, we got it? All right. Who remembers what this upside down Y is called? Anybody? Lambda. So this is a Greek letter. Lambda. What's it stand for?
Frequency?
Not frequency. What's the other one? Wavelength. Okay. And what are the units on wavelength? Good. Meters. All right. So then we have this guy up here. Another Greek letter. What Greek letter is that? Nu. Nu. Stands for what? Frequency, I see. And what are the units on frequency? Hertz. Which mean what?
Cycles per second.
Cycles per second or what per second?
Wave.
Good. So we're going to, right now, we're going to remember it as waves per second. So we've got all that stuff. So let's just do a couple practice problems. So I'm going to carry my formula over, and I'm going to say a series of waves have a wavelength of 7.2 times 10 to the negative 12th meters per second. What is their frequency? Yes.
Would the wavelength be meters per second or just meters?
Oh, thanks. Meters. Just meters. All right. So this is what I expect to see. I expect to see your formula. Then I expect to see you list the variables like we've always done. And then I expect to see you plug in what you know. So C is 3 times 10 to the 8th meters per second. And I gave you wavelength, 7.2 times 10 to the negative 12th meters. And I ask you about frequency. And then I expect to see you plug them into the linear equation. So I would see 3 times 10 to the 8th meters per second is equal to 7.2 times 10 to the negative 12th meters times nu, or times frequency. My goal is to get frequency by itself. What do I have to do to get frequency by itself? Mathematically, what do I need to do if I want this all alone? Carson, what do I got to do? So I have to get this off this side, right? That means I need to do this. Oops. And I have to do the same thing over here. I don't know why I can't remember that number. Okay, so look at what happens here. This meter, pay attention to this because you will have questions about this. This meter cancels out this meter. So my units become 1 over seconds. That's how I justify the units hertz, because hertz are 1 over seconds. Waves over seconds, cycles over seconds, that second is on the bottom. Punch that in your calculator and see what you get. I guess I should put it in my calculator too. See if we agree. When you have an answer, stand up. You're coming tonight, right?
Yes.
Are you?
I can.
Drake, what is wrong with you?
Wrestling practice. You can talk to Mr. Rose about it.
Okay. No. What, are you coming? Okay. All right, let's see. Who's got an answer they want to share? Nobody wants to talk today.
I'll share.
Okay, Connor, share.
I got 4.16 times 10 to the 19th.
Hey, that's what I got. How many of you got that?
I got it.
All right. So, if you didn't get it, the first thing I want you to do is check how you put it into your calculator. Did you divide through by this 7.2? And if you did and you didn't get it, did you put a parenthesis on the end? Because that's what usually gets people. If you didn't get it, punch it in this way. I'm going to tell you exactly how to put it in your calculator. Hit 3 times 10 to the 8th and then hit enter. Really do try this if you didn't get it. 3 times 10 to the 8th, enter, divided by parenthesis 7.2 times 10 caret negative 12 parenthesis. See what you get. Did you get it that time? Okay, so that's what it is. All right, I'm going to give you another one to try. I'm not going to do it. I'm going to let you do it. Calculate the frequency. No, let's do the wavelength. Calculate the wavelength of a wave that has the frequency of 4.8 times 10 to the negative 16th hertz. All right, I want you to work all the way through it. And when you're all done, I mean, like, show me step by step. And then when you're all done with an answer, stand up. When you're all done, stand up. All right, I want you to find somebody to check your answer with. Those of you who didn't already do that.
Nope, you got it. That's not scientific notation.
Oh, no, right.
Check with somebody, it doesn't matter who.
And the big one.
What'd you get, Jacob, that doesn't make sense?
Well, the first time I tried it, I got 6.25 times 10 to the 23rd, but that does not make sense.
Why not?
Well, I just would not expect that to be the size in meters of a wavelength.
Okay, so, let's keep in mind, I'm just making up numbers right now. So do you feel, did you mathematically put it correctly into your calculator? Yeah, you have the right answer. Does it seem super large? Yes, it does. Does it seem realistic? Maybe not. So you're not incorrect in that summation. You are correct in your answer, though. Okay? So all we really needed to do is the math that we did on the last one. 4.8 times 10 to the negative 16th on this side. 4.8 times 10 to the negative 16th on this side. This should be in meters. We end up with a wavelength of, I'm trying to remember now, 6.25 times 10 to the 23rd meters.
But wouldn't we have to round it to 6.3?
Yeah, if we were rounded to the tens place, we would go to 6.3. Are we good with that, you guys?
Yeah.
All right. Now, one last thing for this unit that I'm going to show you. And this has to do with light and energy. All right. So there was a guy named Max Planck. And what he did through experimentations, calculations, and all kinds of stuff, he basically studied the relationship between frequency and wavelength, not frequency and wavelength, between frequency and energy of light. So rather than looking at frequency and wavelength, now we're looking at frequency and energy. And when he did that, he found a relationship between the two. He found that energy divided by the frequency of light always equaled a constant number. So while he's doing all of his experiments and all of his calculations, he finds out that when he looks at energy and frequency at the same time, the energy of light divided by the frequency of light, when he does that math, he always gets the same number. Constant, what does that mean?
The speed of light. Oh, man.
Stays the same.
It means it stays the same.
Light is constant.
Speed of light is a constant, that's right, Drake. Constant means it always stay the same. Guess what they called this constant?
The speed of light.
No.
Constant.
Yeah, what'd you say, Wes?
Planck.
Planck's constant, yeah. This was called Planck's constant. And the variable for Planck's constant, you'll see it either as a capital H or a lowercase h. Most of the time it's lowercase, so we're going to use that. Planck's constant is equal to 6.626 times 10 to the negative 34th joules times seconds. Now, I think we're going to want to stop and put that on our little card for now.
J times F.
Joules times seconds. We'll talk about that in a minute. So anytime I take any kind of light and I take its energy and I divide it by its frequency, that's the number I get, always. It doesn't change, it's a constant. So take that little value, put that on your card. So you've got it tomorrow when we work. Got it on there? All right, so, oh. Have you guys heard of joules before? Okay, good. All right, so this is really what that says, like when I say it in words. This is what it looks like in a formula. Planck's constant is equal to E over frequency. That I don't like. Is that a nice linear equation?
No.
No.
But H times U equals E.
What is this really called?
Nu.
Nu. So, yeah, say that again, Drake. That's good.
H times nu equals E.
That's much prettier. It's much easier to work with when it's in a straight line. Anytime you can take an algebraic equation and make it linear, it's easier to work with. So let's look at this. E equals H nu. So E is energy. Energy is measured in joules. That's from the metric system. And joules are capital J. H, Planck's constant. It is measured in joules times seconds, or J times S. And then finally, over here, we have frequency, measured in hertz, or waves per second. Now take a minute, once you have that all written down in your notes, let's take this formula and put it on your card. Got it?